So, I am thrilled this evening to be able to present Professor Andrew Boothroyd to speak to you on the subject of quantum materials. Andrew is a highly esteemed professor here in the department, works in the sub-department of condensed matter physics, and is an expert on quantum materials. Could we please welcome Professor Andrew Boothroyd?
Thank you very much, Catherine. Quantum mechanics is often spoken of as a theory of the very small, and it's true that the development of quantum mechanics is motivated by the attempt to understand the structure of the atom, 1920s particularly. But when many atoms come together in a solid, it's often the case that quantum effects can be evident even on the macroscopic scale, even on the sort of human scales. And when that happens, one can observe entirely new types of behaviour and exotic properties of materials. And it's these so-called quantum materials which are going to be the subject of this lecture. And as Catherine said, I'm a condensed matter physicist, and as a condensed matter physicist, I study the way in which atoms organise themselves in solids and how that affects the special characteristics that those solids have. And today, we're going to be particularly focusing on electrons in solids and how electrons confined in solids can have very different properties to electrons which are not confined in solids. And I shall introduce the idea and tell you a little bit about what electrons are and how they behave when they're not in solids, and then how they behave when they are in solids. And I'm going to focus on two notions which are quite prominent in the field of quantum materials. These are the notions of emergence and topology, and I'll explain what those two terms mean, and I'll explain how those ideas are transforming the way in which we understand quantum materials. And I'll illustrate these ideas with several examples of particular quantum materials that we've been studying here in Oxford, in which the electrons actually don't behave like electrons as we're familiar with them, but they actually masquerade as completely different types of particles, some of which aren't even known in nature yet. Okay, so before I start talking about electrons in solids, let me say something about electrons that are not confined in solids, that are just free to move around in empty space. And we know from the time of Newton, electrons have got mass, and therefore we can talk about the kinetic energy of the electrons, which is just given by a half mv squared. Or if you prefer, we can re-express that in terms of the momentum of the electron as p squared over 2m. And one of the ways in which one can characterize particles which have got mass is by the relationship between their kinetic energy and their momentum, which is just this quadratic relationship, and therefore this is just a parabola on this type of plot. Einstein, of course, revised Newtonian physics and considered the case when particles move very close to the speed of light. And one of the things that comes out of his theory is that the relationship between energy and momentum is no longer a quadratic relationship like this one, but instead eventually tends towards a linear relationship, so that for particles which are highly relativistic, this graph of energy versus momentum becomes a straight line like this. And of course, the Newtonian part of this curve is right down at the bottom here at very, very small energies and very, very small momenta. So really there's a little bit of a parabola down here, which we can't see. Still thinking about free electrons, Dirac showed that free electrons actually have some other properties. Dirac, of course, was a famous British physicist, and in 1928 he discovered an equation which defines or describes electrons which is both consistent with special relativity and with quantum mechanics. And there's two features that came out of his equation. One is that electrons have a property known as spin, which is a little bit analogous to a rotation. But it's different from a conventional classical rotation in that the electrons can only have rotation in either a forward direction or a reverse direction. They can't take arbitrary values of the electron spin. So in fact, we need to revise this curve a little bit and take into account that for every momentum, there are in fact two different states of the electron, one with a spin forwards, if you like, and one with a spin backwards. And the other consequence that Dirac discovered in his equation was that electrons can have negative energy. There are negative energy solutions to Dirac's equations, and this introduced the idea of antimatter. So in the case of electron, the antiparticle would be the positron, and they would be represented on this diagram as solutions down here in the negative energy axis. So this is what we know about electrons which are not confined in solids. What happens when we put them in solids? Well, this is a very simple classical picture of how electrons behave in metals. So this diagram is supposed to represent a metal bar to which we've connected a battery, and so a current flows, and the current is due to the motion of the electrons travelling through the metal. And in the simplest picture, we can think of the voltage as simply accelerating the electrons in this general direction. They collide sometimes with atoms which are vibrating, and that randomizes the motion of the electrons, and then they travel for a bit further, they collide with another atom, and randomizes the velocity again, and so on. And eventually the electrons make their way from one end of the metal to the other. I like to think of this as a bit like if you're at a party, and there's lots of people on the dance floor dancing away, and you want to get to the bar, which is at the other end of the room. And the only way to get there is to keep on avoiding people, and you keep on bumping into them, and eventually you sort of wind your way from where you are to the bar at the other end of the room. This is a bit like electrons moving in the metal. This picture, of course, it misses a lot of detail, but and is not the modern picture we have of electrons in solids. Excuse me, but it does explain some things. It explains, for example, Ohm's law. So in this picture, the current that you obtain is exactly proportional to the voltage, and the constant of proportionality, of course, is resistance. And it also gives an explanation, at least a qualitative explanation, of how the resistance of a metal behaves with temperature. So on this diagram here, I've reproduced the resistance, or actually resistivity, which is like the intrinsic resistance of the metal, in this case of copper, as a function of temperature, starting from room temperature, which is in absolute units 300 Kelvin, and then going all the way down to very close to absolute zero. And you can see that what happens is that as you increase the temperature, the resistance of the metal just systematically increases with temperature, like this. And that can be understood in this picture because as you increase the temperature, the atoms vibrate with greater amplitude, have more kinetic energy, and that means that they scatter the electrons more readily, which causes greater resistance. Now, of course, this picture completely neglects quantum mechanics. And the first person to attempt to apply quantum mechanics to electrons in solids was a Swiss physicist called Bloch, Felix Bloch. And quantum mechanics, one of the important insights from quantum mechanics is that particles can sometimes behave like waves. And in quantum mechanics, this is accounted for by assigning the particle what's called a wave function, which satisfies a wave equation. And what Bloch did was he solved the wave equation for an electron, a single electron, in a periodic crystal. That means a solid which contains irregular repeating arrays of atoms extending for many, many atoms in all directions. So that's what Bloch did. And his solution has several features. One of them is that if you look at the energy momentum graph predicted by Bloch's theory, in fact, the general trend is a little bit like what you'd expect for a free, unbound electron. It has this parabolic shape. We're assuming here that this is non-relativistic. So it has this parabolic shape predicted by Newton's kinetic energy. But you can see that there are parts of the graph where there are breaks in it. And in those regions there, those particular momentum values, there are actually no energy states at all in his solution. And we can get some sort of a notion as to why this is by thinking of the electrons as waves. But instead of looking at electrons, let's look at a kind of wave that we're more familiar with. This picture here is an image of a ripple tank. So these are water waves on a ripple tank. And on the left-hand side here, we just have a series of plain wave fronts of the water waves. And then in this red line here is a barrier, which has two very small holes in it. And these holes let some of these waves go through, which form a sort of point source of waves emerging from the two holes here. And on the right-hand side, you can see that those circular waves that emerge, they add together, and in certain directions they reinforce one another. This is, of course, is because the maxima and the minima of the waves from each of these two holes are in phase, they're in step, and so they reinforce. And in between those regions, there are regions where there is a cancellation, and so the maxima of the waves from one source cancel out with the minima of the wave from another source. This, of course, is a water version of Young's famous double slit experiment. And of course, we can also do this experiment not just with water, but with light, because light is a wave. And I want to show you a few examples, just for fun, really, of how you can get similar kind of interference effects with light. So I have here a laser pointer, like I was showing there. And here I have a small metal disc which contains a piece of glass that contains many, many very, very finely spaced ruled lines. So rather than having just two sources of light like I had on that picture of the ripple tank, this has many, many sources of light. And if we put this in front of a laser pointer, I think what you can see is that the slits actually break up the beam of light into a series of discrete points. And the reason why that is because we're getting constructive interference only in very, very special directions. And in between those directions, you can see there's no visible intensity of the light, so that's where the light cancels out. And coming back to this picture of the gaps in this electron curve, the fact that you get forbidden regions where the light cannot, is destructively interference, essentially that's the origin of why you get these breaks in this curve. So there's a destructive interference effect that gives us no states around here. And I have some other examples of how to do this experiment. One can use household objects like a CD, because a CD contains many, many finely spaced lines. And if you put a CD in front of a laser pointer, can you see that I have a central point, but on either side there's a couple of satellites, and those correspond to the constructive interference satellites from the light diffracting or interfering from this CD, and you can see you can actually make them rotate around as you go around the CD. And finally, I borrowed the tea strainer from our teapot at home. Tea strainer just contains a very, very fine mesh of wire. It's like a wire grid. And if you shine a laser pointer through that and just look at that wall over there, so there's the laser pointer. If I put this in front and try and keep it steady, I think what you can see is that there's a series of, quite close together, a series of spots that decay away from the center. So this is the interference pattern from the little holes that form a sort of square pattern inside this tea strainer. Okay, so that was digression. Going back to Bloch's solution of electrons in metals, so one of the things that quantum mechanics tells us is that if you have more than one electron, Bloch's solution was just for one electron. If you have more than one electron, what you have to do is you have to fill up all the states described by this curve here, starting from the lowest energy, a bit like filling a glass with water, until you've used up all the electrons, and then this will be the highest filled state of the electrons. And it's actually the highest filled state of the electrons which is the crucial states for determining the property of the material. And I like to think of this as a bit like a row of cars which have been stacked together like this, but they've been stacked together so closely that only the cars which are at the front of the queue, so to speak, can move. Only these can drive out and move along this road and maybe go and park somewhere else. All these ones back here are trapped in position. They can't move. So the electrons down here are like these trapped cars. There's nothing you can do with these. It's only these ones at the top here which can move around. So if you apply a battery, for example, all the electricity will be carried by these electrons at the highest energy states here. So the properties of the materials will be dominated by these electrons. And this actually gives us a very nice explanation as to why some materials are metallic-like and other materials are insulating, because if, for example, we have a picture like this where the highest electron states are in a part of the curve which just looks much like a free electron, the free electron parabola, then these electrons will behave much like free electrons and will just propagate through the materials like a metal. But if, on the other hand, we have more electrons in the solid and they actually fill all the way up to somewhere in a gap like this, then there are no states for these electrons to move into. They're completely locked, trapped in place, and this material will be an insulator. So Bloch's theory was very successful in its time for explaining why some materials are metals, some are insulators, and even why some are semiconductors. And this kind of formulation gives us a perfectly satisfactory description of many of the kind of important electronic substances that we use in everyday life for the kind of devices and gadgets that we use all the time to keep us alive. Now, even at the time of Bloch, there was a phenomenon that was known which actually cannot be described by Bloch's theory, and this phenomenon is superconductivity, discovered in 1911 by Kamerlingh Onnes. And superconductivity is a property of certain metals which, when you cool them down to low temperatures, transition into a state which has got absolutely no resistance. So taking niobium, for example, this is a plot of resistivity versus temperature on an absolute scale. And you can see as you cool it down, the resistivity drops and drops, and then it sort of looks like it's tending towards about 4 times 10 to the minus 8 on this scale. But all of a sudden, at just below 10 Kelvin, it drops precipitously to 0, and this really is 0 below that temperature there. So this phase here, this state here, is a superconducting state. And superconducting have a second important property related to this, actually, which is that if you apply a magnetic field to them, they expel all the magnetic flux from the interior of the superconductor. So if you put a superconducting sample, which is like this piece of black puck here, on top of some magnets, the magnetic field lines cannot pass through this superconductor. They have to actually bend and go around it. And this bending of the lines of magnetic flux creates a force, which in this case is sufficient, gives you a sufficient lift to levitate the superconductor above the magnets. So these are the sort of experimental phenomenology of superconductors. That's the two most important ones anyway. And Bloch actually, after his PhD, when he solved the equation, the wave equation for the electron, he actually spent a whole year trying to apply his theory to explain the phenomenon of superconductivity. And he didn't succeed. In fact, it was a hopeless failure. He did manage to write down one theorem, which is now called Bloch's first theorem of superconductivity, which is valid and which is legitimate and correct. But he failed to make a genuine theory of superconductivity. And actually, he after this year, he expressed his frustration in a sort of informal kind of second theorem of superconductivity, which goes like this. The only theory about superconductivity that can be proved is that any theory of superconductivity is refutable. In other words, whatever theory you come up with is going to turn out to be wrong. And actually, this has been a very good guiding principle for those of us who work on superconductors. So let me come back to the question posed in this lecture, what are quantum materials? So one way we can think about quantum materials are these are materials in which the electrons, because of quantum effects, don't behave like free electrons. And the way in which we are thinking about quantum materials today comes into two kind of classes of materials. One subclass of materials are materials in which emergence is an idea which is being applied to them. And emergence applies, I explain what this means later, but emergence applies to systems in which the forces between the electrons cannot be neglected. So in Bloch's theory, the electrostatic forces between the electrons is totally neglected. But there are materials which exhibit phenomena called emergent phenomena where the forces cannot be neglected. So that's one class of quantum materials which are of interest today. And the other class of quantum materials are called topological materials. And these are materials where the geometry of the electrons, or the geometry of the electron's wave function, to be precise, is not the same inside the material as the geometry of a wave function in free space or in empty space. And I'll give you some examples of both of these systems in due course. So let me say a little bit about emergence. Emergence is a term that's used to describe large-scale patterns of behaviour in many particle systems, so many particles together, which cannot be easily predicted based on just the local short-range forces between the particles. So this is a bit like, human beings. If you put lots of human beings together, they can sometimes behave in very strange and unpredictable ways just because of the kind of collective nature of the crowd. So an example in sort of nature, I suppose, is a snowflake, which, as we know, is made up of lots of ice crystals. Now, sometimes it's said that all snowflakes are different, but yet all snowflakes are fundamentally made up of water molecules, H2O. And we know pretty well, physicists understand pretty well what a water molecule looks like and how water molecules interact with one another, what the forces are. But just knowing those things, it would actually be very difficult to predict the precise shape of a snowflake. So this, if you like, is this shape here is, if you like, is an emergent phenomena that arises out of many, many water molecules interacting together in this cooperative sort of way. And in condensed matter, there are huge numbers of different types of emergent phenomena, and these are interesting, intellectually, but they can also be very important because when you put together many, many particles and you have them acting cooperatively, when they act cooperatively, if you like, in unison, then even a very small stimulus can generate a gigantic response of the system. And this is the kind of effect which is very useful for practical materials. Often you want a material, for example, where if you just shine a small amount of light on it, it transforms from an insulator to a metal, for example. This is a very useful material for practical applications. And it's, this phenomenon is a bit like teamwork. If you have a large number of people working together in a team, then the effect of the whole is greater than the sum of the parts. So in a sense, that's why you get enhanced responses in emergent phenomena. And one of the big ideas in quantum materials at the moment is not so much the static arrangement of the atoms, but what the kind of low energy motion of these emergent states are. And one of the big ideas is that it's been found that in many systems, the kind of low frequency or low energy oscillations or vibrations of these large-scale patterns, these emergent patterns, can often be described in very, very simple ways, just in terms of the excitations of particles or the motion of particles. It's a bit like, so with this millipede, of course a millipede is an incredibly complex organism, but the motion of a millipede can really be summarized in terms of a simple sinusoidal wave-like motion of its legs. So you can sort of strip away all the messy complexity of what a real millipede is, and in terms of its motion, just think about a simple sine wave-like motion of the legs. So this is this idea of what's called quasi particles. So the idea that a complex system can be replaced by a very simple picture in terms of some kind of particle or wave-like motion which can strip away all the messy details of the system. So I'll give you some examples of quasi-particles shortly. Now, okay, so returning to quantum materials more specifically, even before superconductivity, quantum materials were known of. They weren't called quantum materials, but they were known. And in fact, the first example, I suppose, was magnetism. Even the Greeks and the Chinese, the ancient Chinese, knew that in magnetite, a mineral magnetite, you could put the particles together and they would stick together. And this was due to magnetic forces. And of course, you're all familiar with bar magnets and with the pattern of lines of force that you get, for example, by sprinkling iron filings. If you look at a ferromagnet on the atomic scale, what we actually have is an array of atoms like this, and each atom carries a spin. And there are forces between these spins. These spins actually behave a little bit like a tiny atomic-sized bar magnet. And there are forces between these spins, which in the case of a ferromagnet, makes them want to line up all parallel with one another like this. So this is a picture you should have of the atomic behaviour of a ferromagnet. And there are other types of arrangements of atomic scale bar magnets in different materials which have different patterns. Like this one, for example, is called an antiferromagnet. In antiferromagnets, there's actually each atomic bar magnet, if you like, is pointing in an opposite direction to its neighbour in all directions. So in fact, there are as many bar magnets pointing up as there are pointing down. So overall, there is no net magnetization of this piece of antiferromagnet. So the question then arises as to how do you know you've got an antiferromagnet if it's got no magnetization? So the kind of modern way of finding and identifying an antiferromagnet is to shine a beam of particles, usually beams of neutrons or X-rays, at this sample, which is an antiferromagnet, and to look at the distribution of the particles which are scattered from the sample. And this periodic arrangement of bar magnets acts a little bit like a diffraction grating, like these ones I was showing you before with the laser pointer. So you get sharp peaks, sharp bright beams coming out of the sample, and by looking at the distribution of these beams, you can infer the pattern of magnetic moments inside the solid. So this is a sort of modern way of getting at what the arrangement actually looks like in solids. And many of us here who work on quantum magnetism, quantum materials, we use this kind of technique to identify complex emergent phases in solids. And these are not techniques that can be just set up in the laboratory here. To make these very powerful, we use, there are national facilities for doing these experiments. Many of you will know that on the Harwell Oxford campus, about 10 miles south of Oxford, there are some condensed matter facilities. In fact, there's a neutron scattering facility called the ISIS Neutron and Muon Facility, which is this series of buildings here. And there's also the diamond light source, which is an X-ray synchrotron, which has got all sorts of X-ray techniques associated with it. So we use these facilities for identifying and discovering new quantum phases. There are actually other facilities available to UK researchers. This picture is a picture of a mountainscape near to Grenoble in France. And somewhere on this picture there is the European Photon and Neutron Science Campus. It's actually here. So in this, where these two rivers meet, you can see there's an X-ray synchrotron here and there's a neutron scattering facility again. And UK users can go and use these facilities to do their experiments. All right, so coming back to some specific examples of quantum materials, I want to talk about, first of all, about some materials in which it has been found that there is some motion, some excitations which behave a little bit like magnetic monopoles. Now, what are magnetic monopoles? So here's another picture of a bar magnet with a north and a south pole. And if we could isolate this north pole from this south pole, then this would be called a north monopole and a south monopole. And you might think that you could do that by simply cutting this magnet in two, like that, but in fact you can't. If you cut a magnet in two, what you get is you simply get two bar magnets of half the size. And the reason why that is because, as I said earlier, the bar magnet consists of lots of atoms, each one which carries its own tiny atomic scale bar magnet, and so this looks exactly the same as a big bar magnet. So we just get two individual bar magnets. How do you know if you have discovered a magnetic monopole? Well, you know because a magnetic monopole, which would just be an isolated, say, north pole like this, the magnetic field or magnetic flux coming away from that monopole always comes outwards, so that if you were to construct, say, a spherical surface around this monopole, there will be a net amount of flux coming out of that surface. Whereas if you were to construct a sphere around a bar magnet, so this is called a dipole, so with a north and a south pole, then there would be a net flux coming out of the north end, the north pole end here, but that's exactly compensated for by a flux going into the south pole. So in fact, that there would be zero net flux coming out of this spherical surface that we've constructed around here. So that's how you can tell when you've got one. And people have been searching for monopoles, free monopoles, for many years without success. So there's nothing in physics that's in theory that says you can't have an isolated magnetic monopole, but so far none has been discovered experimentally. But the searches that have been done are based around this idea that you have a net magnetic flux coming out of a volume like this. So we'll see. We'll see if they've discovered one day. But in fact, magnetic monopole-like particles have been discovered, but they've been discovered confined inside solids. And I want to explain how that works next. The material of interest is a material that's called spin ice. And so chemically, this has this chemical formula. And this diagram here shows the way in which the atoms are arranged in the unit cell. And I'm not going to walk you through the horror, which is this structure. But I would like to focus on these blue atoms, or the atoms represented by these blue spheres here. These are atoms of holmium, which, if you're not familiar, is one of those elements that's usually represented in the two rows at the bottom of the periodic table. So it's one of the ones with the funny names in those rows down there. And if you look at this diagram, the holmium atoms in this structure they actually form tetrahedra, regular tetrahedra, which are joined together at their vertices. So you can see this tetrahedron and that tetrahedron meet at that vertex there, and these two meet at this vertex, and so on. So inside this complicated structure, there's a network of these tetrahedra joined at the corners. And one thing that we know about these holmium atoms is that they carry a magnetic moment, so they act like a little atomic bar magnet. We can do experiments on this. This is not a naturally occurring substance. You can't dig it out of the ground, but you can grow it in the laboratory. And my colleague Prof actually was one of the first people here in Oxford to show how you can make very high quality single crystals of this spin ice material. So this is holmium titanate. You can see it's a rather nice brown, yellow, red colour, and it's sort of semi-transparent. And this is about 5 centimetres long. So this is the type of sample that we do our experiments on. Now, why is it called spin ice? I've just picked out one of these tetrahedra from the previous diagram, and on the corners of the tetrahedra there are these holmium atoms carrying a little atomic level bar magnet, and this arrow is representing the bar magnet, just like a north and a south pole. And what is found is that because of the particular chemical environment of the holmium atoms, these bar magnets only ever point either towards the center of the tetrahedron or immediately away from the center of the tetrahedron like that. So they always point along the line from the corner to the center of the tetrahedron. They can't point in arbitrary directions. And in addition, the forces between these bar magnets makes it so that the most stable arrangement of these four bar magnets on the tetrahedron is when two of them are pointing into the center and two of them are pointing away from the center. This is the most stable arrangement which it would like to have. And there's a strong parallel actually with the way in which water molecules are arranged in ice. So I showed a water molecule before, 2 hydrogens and an oxygen in this shape. And in water ice, you can think of these as being at the center of a tetrahedron with the bond from the oxygen to the hydrogen pointing towards the vertex of the tetrahedron. So in this case, the 2 hydrogens are on the line from the oxygen to 2 of the vertices. And then other water molecules stack themselves around so that in the direction in which there is no hydrogen atom close to this oxygen here, there will be a hydrogen atom close to one of these neighbouring oxygens. So around an oxygen atom, there's always 2 near hydrogen atoms and 2 more distant ones. And in fact, this arrangement was first described by Burnell and Fowler in Oxford a long time ago, more than 50 years ago. These are called this idea that there should be 2 short hydrogen atom bonds and 2 long hydrogen atom bonds. They call the 2 in, 2 out rule. And you can see the parallel with spin ice. We can think about these arrows as being a bit analogous to these short bonds. So there are 2 in and 2 out, like this. So that's why it's called spin ice. Now, the question is, well, what happens if we take spin ice and we put it in its most stable arrangement where all the tetrahedra have 2 spins pointing in and 2 spins pointing out? What happens if we now make a blemish in this pattern, and we, for example, take this spin here and we turn it around. And this can happen in reality, for example, by warming up the substance so that there's enough energy for the spin to just flip around just due to thermal agitation, or you can make it happen by shining light in the system or something like that. We just make this spin turn around. So if you do that, then what it means is that now this tetrahedron here has 3 spins pointing in and 1 spin pointing out. And if you remember, my definition of a monopole is a bit in terms of taking a volume or a spherical surface surrounding the monopole and saying if you have a monopole, if you have a net flux of magnetic field either going in or out into that sphere, you can see that this tetrahedron here, there is now 3 spins pointing in, so there is like a net magnetic flux going into this tetrahedron. So it's a bit like as if we now have a monopole at the centre of this tetrahedron. And if we call this a north magnetic monopole, then the neighbouring tetrahedron, because this spin is flipped, has now got 3 spins pointing out and 1 spin pointing in. So this has now got a south, if you like, magnetic monopole. So we've generated a north-south monopole pair. Moreover, if this monopole can now move, because if we take this spin here on the vertex that's common between these 2 tetrahedron, flip that spin, the first tetrahedron now has 2 in, 2 out spins, but this tetrahedron will now have 3 spins in and 1 spin out. So effectively, the monopole has moved from here to here. And now if we flip that spin, then that effectively moves the monopole from here to here. And likewise with that spin. So eventually you can get a situation by a series of contiguous spin flips. We've generated a monopole pair, and one of those monopoles has moved away from its original place to somewhere else in the structure. And that's because these tetrahedra form a network of connected tetrahedra. And in fact, the energy of separation doesn't depend upon the path taken. You could take a path through some tetrahedra over here, like this, and get to this point. The energy would be the same. So in fact, it's been shown theoretically that the behaviour of these spin flips is exactly consistent with these 2 objects, these 2 defects, if you like, in the magnetic arrangement as being magnetic monopoles. But I emphasize these monopoles here are confined in the solid. You can't take them outside the solid. They only exist as long as they stay inside the solid. How do we know that this is what happens? How do we know that this is all true? Well, the first thing to establish is that the stable state of spin ice is this 2 in, 2 out. You need to understand that, you need to establish that it obeys that 2 in, 2 out rule. And this can be done by scattering beams of neutrons, like I was explaining earlier. And I'm showing here actually an interference pattern obtained by shining neutrons at one of these holmium titanate samples and measuring the distribution of the scattered radiation, as in this case in a plane. And then one can work backwards and infer what the arrangement of the spins is that gives this pattern. And I've represented that here actually by making a simulation of what you'd expect the interference pattern to look like if you had in fact the 2 in, 2 out structure. And you can see that the model, the simulation, has a strong resemblance to the experimental data. So this confirms that the stable state, this natural state of spin ice is with 2 spins in and 2 spins out. And then the question is, how can we prove that by creating a blemish, by turning a spin around, how can we prove that that actually behaves experimentally like a gas of monopoles? Well, there's actually several ways to do this, but one way in which it was done in the early days of this field was to measure the heat capacity. The heat capacity of a solid measures essentially how much energy it requires to warm up the solid. And it's essentially measuring the number of particles or the number of excitations present in the solid. So this is the experimental data, these squares. And this blue line is the curve that you would get if the idea of magnetic monopoles as being if you like, the fundamental dynamical modes of the system is correct. And you can see it agrees pretty well with experimental data. And the red curve is actually another type of theory which just assumes that this behaves like a very conventional magnetic material without any fancy monopoles, and you can see that doesn't work so well. So this and other kind of experiments confirm that this picture of all the complexity of this horrendous crystal structure with all these holmium atoms and spins all over the place can simply be reduced down to the idea of a weakly interacting gas of monopole particles confined in a solid. And this is actually a very satisfying idea intellectually, but it's also potentially quite a useful idea practically, because although these monopoles are confined they only exist as long as they're confined in the solid, you can actually do stuff with them. If you apply a magnetic field to spin ice, then you can actually make these monopoles move. You can drive the north pole to one end of the material, the south pole to the other, and that effectively carries a current, a monopole current, with it, which then has an electric field associated with it. So you can actually create circuits where instead of electricity flowing through an electric current, where the electricity is flowing through a monopole current, if you like, a magnet current. And this field has been called magnetricity for obvious reasons. And it's actually there are advantages of using magnetic particles to carry the current instead of electrical particles. The most important of which is that nothing is actually really physically flowing. There's no mass actually flowing in a monopole current. It's just a series of spin flips. And so there's actually no resistive heating. There's no heating of the solid due to resistance. In a normal metal, when you pass a current through it, it warms up. But this material has got essentially negligible resistance to it. So you can imagine that you can make electronic circuits which have much lower power dissipation than conventional circuitry. Okay, so I want to move on to the second of these big ideas, which is influencing this field, and that's the idea of topology. Topology is a branch of geometry which deals with the question about whether you can continuously deform one shape into another shape. And this, of course, is a simple example. If you take a cylinder of paper like this, and you take a Möbius strip, which is a cylinder which has been twisted once, then you can't continuously deform this one into this one. There's no way you can do it. The only way in which you can make this turn into this is actually to rip it, make a twist, and then glue it back together again. So this actually is very invasive. That process is very invasive. And the reason why topology has become important in condensed matter is because it's been discovered that there are situations where you can start with a material which has got one type of state, and you can introduce somewhere in the material locally a defect which is topologically distinct from, if you like, the matrix, the host material. And once you've introduced that defect, because it's topologically different, it takes a huge amount of energy for it to relax back into the kind of surrounding matrix structure. So it's, if you like, it's locally stable. And you can see this might be important because it means that you can create states which are stable against weak perturbations. So you can create new states in materials. And this is one example of a topological material which is very topical at the moment. This pattern of arrows, coloured arrows, is called a skyrmion, or it's representative of a skyrmion. Skyrmions they were first proposed in the 1960s by somebody called Tony Skyrm, who actually spent some time here in Oxford and also worked for many years at the Harwell laboratory, where he came up with this idea. Turns out, so his idea was applied to the nucleus as a description of the nucleus of atoms. It turns out that probably hasn't yet been proven to be correct, but the same idea has actually been found to be useful in certain types of ferromagnets, which is what's represented here. So the red arrows on the outside, you can see all these are parallel to one another. So this is just like a ferromagnet, and if I imagine that this pattern continues all the way around here. So all these spins, there'll be lots of red spins with the arrows pointing upwards. And what we've done here is we've just introduced a defect in this perfect ferromagnetism in which all the spins kind of turn over into a point. So it's a bit like putting a dent in this ferromagnetic pattern. And the claim is that this defect is topologically different from the surrounding ferromagnetic material. And to see why this is, it's useful to take a section through this pattern across a diameter, which is what I'm showing at the bottom here. So you can see that as a function of distance, the atomic bar magnets sort of tumble. They rotate first of all clockwise, and then they rotate anti-clockwise back again like that. And now if you think about trying to continuously deform this pattern back into the original ferromagnetic pattern, so if we look at this section again, what we'd have to do is we have to slowly rotate these spins on the left of center side here anti-clockwise so that they all point upwards. And on the right here, we would slowly rotate these spins clockwise, again, so that they all point upwards. But a problem occurs actually with the central spin here, because if you make the central spin go with these ones on the right, so it rotates that way, then actually it will actually rotate against its neighbouring spin to the left here. And you'll get a situation where these two spins will actually end up being at right angles to one another. And because the material, the spins they favour being parallel, being at right angles is a very unfavourable configuration for these spins. So in fact, it costs a lot of energy to rotate these spins back into the vertical situation. And you can sort of represent that here on this diagram of energy versus, I suppose, distance in this scale here. The energy of the original ferromagnet is the lowest energy because that's the stable arrangement of these spins. And the skyrmion, which is this defect here, has got a higher energy. But in order for the skyrmion to relax back into the ferromagnet, you have to take it over a very large energy barrier, whichever way you go, and that corresponds to these two spins turning in an unfavourable way with respect to one another. So these skyrmions are very stable defects, and in fact they're being discussed. There's a big project in the UK on skyrmions involving groups in Oxford, and these are being discussed in terms of, for example, recording information, because once you've recorded it, it's a stable pattern because there's topological stability. I wasn't going to talk about skyrmions in any detail. I want to talk about another type of topological quasi-particle, which can be found in quantum materials, and these are called Weyl fermions, after this man here, Hermann Weyl, a German theoretical physicist who solved the Dirac equation for a special case of an electron, a hypothetical electron which has zero mass. So of course electrons have mass, so this is not a real electron, but he found a solution for a particle which has got zero mass. And he found that this particle has got different properties to free electrons. What he found was that, first of all, of course, it's relativistic because the particle's got zero mass. But secondly, the spin, he found that there's actually a coupling between the spin and the direction of the momentum, so that the spin either always points parallel to the direction of the velocity or anti-parallel to the direction of the velocity. And if it points parallel to the direction of the velocity, that's a bit like something rotating along the direction it's moving. So it's a bit like a helix, say moving clockwise. So that'd be like a left-handed helix. And if the velocity turns around and the spin turns around, that's still a left-handed helix because all we've done is turned around. But you can also have these particles where you have a right-handed helix, so the spin is now opposite to the momentum. And again, if you turn around, this is still a right-handed helix. So in fact, these Weyl fermions, so this is not a property that ordinary electrons have. It's a special property of what's known as these Weyl fermions. And for a while it was thought that neutrinos were examples of Weyl fermions, but it turned out fairly recently that neutrinos have actually got mass, so they can't be Weyl fermions. And so far, there are no confirmed examples of Weyl fermions in nature. I mean free Weyl fermions that are not confined in solids. However, a few years ago, 4 or 5 years ago, there were proposals that certain materials, you could engineer the electronic structure of these materials so that the energy-momentum relationship looks exactly like the Weyl, what is predicted by the solution of the Weyl equation. And in fact, the first example of such a material was discovered in 2015, so relatively recently. In this compound here, Tantalum Arsenic, it was discovered by several groups around the world independently, including one here in Oxford. And this data here, this plot here, is just an example from one of the groups of, if you like, proving the proof that this that the electrons in this material behave like Weyl fermions. This is the energy momentum graph, which has been obtained experimentally by a technique called angle-resolved photoemission spectroscopy. So this is a technique which directly measures the electron, the energy momentum dependence of the electrons inside a solid. And you can see that you have this kind of inverted V-shaped graph showing the energy momentum, and actually there's two side by side. And this particular technique can only measure the electrons in occupied states. So that's the occupied states are the ones that are, if you like, with energies down here below zero. These are all unoccupied states. And if you were able to measure those, this pattern will be symmetric. So you get a V shape going up as well. So you can see that the energy momentum graph looks just like the graph predicted by the solution to the Weyl equation. And indeed, with this technique, you can actually show that these particular electrons, or Weyl fermions, have one-handedness, and these ones have the opposite-handedness. So this was the experimental proof of the existence of these so-called Weyl fermions. So these are emergent particles which are not yet known in free space as fundamental particles. And finally, before I stop, on the same topic of Weyl fermions, it turns out that there's a second way that's been predicted in which you can generate these kind of exotic particles, and that is in materials which have magnetism. So materials in which there are some atoms which carry these atomic scale bar magnets. This is one material that we've been working on recently, europium, cadmium, arsenic. This is not a good material to swallow, by the way. This is very poisonous. But the europium, this is another of those elements in the bottom two rows of the periodic table. This carries a magnetic bar magnet, if you like. And in this particular structure, at low temperatures, these bar magnets arrange themselves so that there's a plane of spins pointing one way like this, and then there's an adjacent plane pointing the opposite way, and so on. And if you look at the electron band diagram, the energy momentum diagram for this material, which is a metal, what you find is that the diagram looks a bit like a parabola. So it looks very much like a free electron curve. This looks like any electron that could exist in free space. And these are the anti-electrons, if you like, also parabolic. But if you apply a magnetic field and you turn these spins so that instead of pointing in this forwards-backwards arrangement, they all point upwards like this, it turns out that this gap closes. This is a theoretical prediction, by the way. This has not been experimentally verified, but according to theory, this gap closes, and then you get a linear energy momentum plot, which is then consistent with there being these Weyl particles, Weyl fermions. So this kind of approach is what's being worked on at the moment, and it's of interest because you can see that by applying a magnetic field, you can actually generate, you can switch on and switch off these Weyl particles, which is something that may well be of use in practical applications. Okay, so I'm going to conclude now. So in answer to the question posed in the title of the lecture, what are quantum materials? I guess you could say that these are materials in which quantum effects play a prominent role, and also in which the electrons don't behave just like free electrons. And I've explained that the ideas of emergence, when many particles act cooperatively to form large-scale structures, and topology, which is to do with states which cannot be continuously deformed into one another, these are offering new ways of thinking about quantum materials and giving us an understanding as to their properties and simplifying the description of how they behave. And I touched upon some of the experimental techniques that have been used. There's been huge advances in experiment in the last 5 to 10 years, which have made it possible to discover and identify and characterize all these interesting quantum phases and quantum patterns that you can see in quantum materials. And together with advances in theoretical techniques, these are now being used to predict and to engineer new materials which might have useful properties. So thank you very much for listening.